Okay, let's do a reduced mass correction. Let's just see, like, I mean, we derived that, we may never use it, but therefore, let's do a reduced mass correction for orbital period. Let's think about the fact that the sun wobbles a bit, and forget the other planets, right? That gets even more complicated, but wobbles a bit because of the Earth, because the center of mass is a little bit off, and so let's go ahead and assume that the sun is sitting still. If the sun is sitting still and we're orbiting at the average distance between the Earth and the sun, and you can figure out the period, and you can just look this up, right? It's one of Kepler's laws, but you can figure out the orbital period simply by setting the net force between the two objects, gmm over r squared, equal to the mass of the Earth times the acceleration of the Earth, mv squared over r, and use the fact that we know that speed is the orbital distance, 2 pi r divided by period t, solve for the period t, and this is one of those Kepler's laws. T squared goes as r cubed. Okay, so that's the orbital period, assuming the sun's sitting still. But the sun's not sitting still. So what we really need to do, the correction, would be to say that g, mass sun, mass Earth, over r squared, is equal to the reduced mass of the pair, mass Earth, mass sun, over mass Earth plus mass sun times v squared over r. That is the correction. That you correct that. So this is the force between the two, but this is the acceleration of one of them. So you got to do that correction for the acceleration of one of them. The mass is corrected by the reduced mass. And so now this is going to give us a different orbital period. So just go ahead and solve for t squared again. And what we get is a correction to t squared, and that correction is the reduced mass divided by the smaller mass. There's our correction. Let's go ahead and just calculate that correction to t squared, and then we'll see what that is to t, the correction for the Earth and the sun. So without even plugging in the 5.972 times 10 to the 24th and the 6.934, the mass of the sun, 1.989 times 10 to the 30th, just looking at the factors of 10, we get this. Just looking at the factors of 10, I'm going to cancel 10 to the 24th, and what we get is on the order of 10 to the 30th over 10 to the 30th plus 10 to the 24th. So you can see the correction, if the mass of the Earth was 0 compared to the mass of the sun, the correction would be 1, right? There would be no correction. Because this is a factor, right? We're multiplying t squared. But this is, therefore, it's going to be 10 to the 30th over, it's going to be basically that. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Yeah. It's that. So we get t squared corrected equals t squared times 0.9999, right? The period is slightly smaller than if the sun were infinitely massive and the Earth had 0 mass compared to the sun. And therefore, let's say that t is 1 year. So we get, if I did that calculation correctly, I get that the difference is that the corrected period is 16 seconds less. Yeah, 16 seconds less. So if we take into account the fact that the center of mass of the Earth's sun is not at the center of the sun, the real period, or the corrected period, is 16 seconds less than treating the sun as if it's fixed in place. Don't forget that, right? T is 1 year, right? T is 1 year. That's the assumption. Whatever a year is. I mean, a year is actually, in reality, a year is the amount of time that it does take us to go around the sun. So maybe that should be the corrected one, and so therefore, right, that 1 year should be the corrected one, so that the theoretical t should be 16 seconds longer than the actual year that we take to go around the sun.